Claims the mic built in is fine.
Hello everyone, my apologies for being late. My mistake, I lost my Mac to VGA adapter at the conference yesterday and only realized that I forgot it there right before lecture. So let's get started. Today I want to cover 4 topics. Let's see how far we get. Otherwise we'll continue on Thursday. First I want to do some motivation for why we want to deal with probability. Then we'll look at some probability review. That will go pretty fast. If that feels slow, that's great. If it feels fast, then you need to do some more practice. I will probably over the weekend post some exercises on just basic probability onto the course website. And so sometimes the probability review feels fast. Do those exercises to get up to speed. Won't be homework. It's just for your own good. And then we'll look at base filters, which is our first kind of filtering algorithm or general framework for filtering. And if we have time, we'll look at how to model laser rangefinders, and then we'll just start putting that into the base filter next lecture. Okay, so why do we care about probability in robotics? It's 2 parts to it. So 2 different parts. One of them is that often you don't know the state of the robot, and you don't know the state of the environment. And so what you get instead is some noisy sensors that give you some measurement, let's say distance to a wall, maybe some noisy measurement of orientation and so forth. And what you want to do, typically you want to have access to the state to achieve a task. So what you want to do is somehow fuse that sensory information to then get out a reasonable estimate of the state. And probabilistic frameworks are the kind of widely considered right way to get this done. Then another problem is that dynamics of the system is not always stochastic. So for many systems, it's not when you apply a particular control that you know exactly what will happen, because there could be perturbations to the system where you might not have a perfect model of the system. And as a consequence, you have some distribution over what might happen, what might be the state of the next time, and probabilistic reasoning is kind of the framework we'll use and most people use to deal with this. So let's look at 2 concrete examples. You have a helicopter. The state that you often want to work with, which describes the configuration of the helicopter, would be position, orientation, velocity, and angular rate. For none of these do you actually get the information from anyone. What you instead are able to get typically is something like a GPS measurement, which is noisy because it's based on timing how long some wave travels from a satellite, from several satellites to your helicopter. It's based on the clocks on the satellites being synchronized with each other up to very, very high accuracy. And so there's a lot of causes of it being imprecise, and as a consequence you get some noise estimate of your position. Sometimes also a noise estimate of velocity. Then often you put something else on board to get more information. You might put an inertial sensing unit on board, which would have a 3-axis gyro, which is along 3 main axes orthogonal to each other. Ideally, that doesn't mean they build them perfectly orthogonal. You get the measurements of angular rate. You don't get this perfectly because depending on the temperature of your sensor, the reading will be a little different. Same for accelerations. You can put an accelerometer on board. They're supposed to be 3 orthogonal axes. It's not necessarily perfect. These accelerometers, what they measure is essentially how much you resist free falling. So if you're staying put, let's say, in a particular place, then it will measure 1 times gravity upwards, because you're compensating against gravity. If you're free falling, it'll measure all zeros and all 3 axes. Both of these will have a lot of noise due to the helicopter vibrating a lot. So if you look at the sensor measurements coming out of these 2 sensors, it's dominated by vibration of the helicopter, not by the actual signal you care about. And then there's a magnetometer that measures, so the Earth has a magnetic field. It turns out it doesn't change very quickly. It drifts over time, but it drifts slowly enough that you can rely on, if you on a particular day go somewhere and you first measure which direction is the magnetic field pointing here, you can probably use that for a long time to go. The direction it points, it's a vector that points mostly down, but there's a reasonable component that roughly points north. And so that gives you another way of getting some information about orientation. The dynamics is very noisy because maybe you have a very extensive helicopter model that tells you how it would behave, but then even if your model is pretty good, as long as you don't model when the wind will come in from where, there will be noise that you need to incorporate in your model. Often the dynamics you're not able to model very accurately. The engine might have dynamics that are hard to model. The servo motors controlling the blade angles might have some unmodeled aspects. The blades themselves, they're not perfectly rigid. They will flap. That's also really hard to model. So those are all causes of your model not being perfect, and hence you want to somehow capture the imperfections, and a standard way to do it is to assume that there's some noisy process infused into your system. Another example is a mobile robot. So here, the state for, let's say, a robot going around in a building could be position and heading, and you don't get that from any particular measurement. What you get instead is odometry measurements and maybe a laser rangefinder measurement. Odometry, what that does is essentially you have something like, let's say, some sensors like encoders on your wheels, and what they'll measure is how often the wheel goes around. That'll give you some rough estimate of how far your robot has moved if you do that for all the wheels. It's not perfect because the encoders might not be perfect and the wheels might slip. You might also not have a perfect model of how far the wheels are apart, which angle they're at, and so forth. So just getting the odometry measurements will not tell you exactly where your robot's moving. Then laser rangefinder, the way it works is it sends out a beam, and it measures how long it takes for that laser beam to come back, and based on that, it knows the closest object in that direction. It doesn't always work. There's some noise on exactly the measurement it gets. It might also get some interference coming in and get a wrong measurement. It might also be the case that a person walks in front of your robot, and you don't want to model the person because it's very complicated to model how people move around in your building. You just want to model the walls. And then that person crossing the line of your laser will be noise. The dynamics of a mobile robot has some noise because you might not be able to model perfectly how the wheels will interact with the different floor surfaces. There might be some kind of slope to your surface. There might be threading of your carpet that's going in one particular direction, making it easier for a robot to move in one direction and in the orthogonal direction. Might be wheel slippage and so forth. So there's many reasons that it's pretty much impossible to come up with a perfect model for the robot and somehow be able to get away without needing to use probability to handle the noise. So those are two examples, and we'll come back to those two examples in the mobile robot example. We'll come back to very soon, probably next week, and then the helicopter example probably in 3 weeks. Okay. This will probably be the fastest set of slides that we'll do this semester, but just make sure we have all the terminology down and that we have a little bit of a refresher on what we'll be doing in terms of probability. Probability theory has some axioms, and what it says is that for any set of events A, the probability lies between 0 and 1. For any set of outcomes, probability lies between 0 and 1. There is some set of all possible outcomes, which is called capital omega, and the probability of what happens to be one of all possible outcomes is 1. And then the probability of the outcome being in the empty set is 0 because there's nothing in the empty set. If you have two sets, A and B, each of them containing some possible outcomes, then the probability of the outcome falling in the union of A and B is the probability of falling in A plus the probability of falling in B minus the probability of the intersection. So this is to avoid that you double count things that are in the intersection. These are the axioms. You don't need to be able to prove this. It just starts from this. Often the outcome is denoted by a small omega, and in general you can think of the small omega as just kind of the entire state of the entire universe at a particular time that you are considering, and then the set A would be all states of the entire universe in which, let's say, your coin flip came out heads. A is often called an event, and it's essentially just a set of small omegas. Visually, you have some big omega, which is all possible outcomes, and then you have your two sets A and B, and essentially measuring the volume or area, whatever dimension you work in, general volume taken up by A and B. And if you look at it as the volume taken up by A union B, then it's volume for A, B, but then you're double counting this part, you subtract that out. If you play around with the axioms, you can prove simple things, also more complicated things. But there's a simple example. Let's say you want to prove that the probability that the outcome is not in A, so set omega minus A, that's everything omega that's not in A, is 1 minus the probability of A, which logically makes a lot of sense, but which is not in the axioms. You can go back to the axioms and you can say, oh, well, the probability of A union everything but A is the probability of everything, which is 1. And on the other side, we work out the union formula, just the third axiom here. And then this set here is A intersection with everything except for A, so that's phi, the empty set, that has a probability of 0. And then we end up with probability of A plus the probability of omega minus A equals 1. You flip sides for omega minus A and for 1, and you get the final expression. These kind of finger exercises should be very easy, otherwise you should practice. Then random variables. So the idea of a random variable is that you essentially partition your space omega of all possible outcomes of your experiment in a way where you have different labels, let's say x1, x2, x3, and x4, and they're non-overlapping sets. And so you have a capital X, which is a random variable, and you say you can take on a countable number of values, in this case x1 through x4, and the probability for your random variable being taken on an outcome xi corresponds to the volume that you carved out for that particular region. Then we'll call the probability of a particular outcome for a random variable a probability mass function. And a simple example is, let's say if you had only 2 possible values for a random variable, let's say for a coin flip, you have the entire universe is omega, and then you split it into 2 parts, x1 maybe on the left, x2 on the right, and then the probability of x1, which is heads, would be a half, and for x2, which is tail, would be half. So that's the general principle. If you have continuous random variables, the problem becomes that if you're wondering, well, there's a continuous random variable, it's a probability of having a particular value, the probability ends up being 0. Let's not do that. Probability ends up being 0. Because if you assign a finite probability for a continuous random variable to every value, then the total probability would be infinite, because there's infinitely many values that you can find on this axis. So what people do is they say, let's work with a different formalism, which is called probability density function. And now you define the probabilities through integrals. So you say the probability of x lying in some interval, let's say AB, would be the area under this curve. And your probability density function, P of x, can now be bigger than 1. It can be anywhere between 0 and plus infinity. Any questions about the basics? Okay. Then what we'll mostly be working with is sets of random variables, so more than one. The simplest case is 2. Let's say you want to reason about 2 variables x and y. Let's say the state of the robot and a sensor measurement you just received. Then we'll define some joint distribution over x and y. And we'll shortcut probability x equal x and y equal y to just p x comma y. And one big thing we'll be playing with when working with distributions over large sets of random variables is independence assumptions. It turns out if you want to represent a distribution over a large set of random variables, let's say 100 random variables, each of them is binary, then you have 2 to the 100 possible outcomes, which is really large. And to describe the distribution explicitly with a table and assigning a probability to each of the 2 to the 100 possible outcomes is not practical. Instead, what we'll do is we'll work with only certain probability distributions, mainly the ones that we can represent fairly efficiently and compute with fairly efficiently. And the key in these representations is independence, and on the next slides we'll see conditional independence. So here's the simplest example. You have a joint distribution over x and y, and let's say you're willing to assume that x and y are independent. By definition, that means the probability of x and y is the same as the probability of x times the probability of y. That's the definition. Then, instead of having a table over x and y, which would be a two-dimensional table, now you just have two one-dimensional tables, one for x, one for y. And in general, the more variables you have, you'll scale linearly in the number of variables if you assume everything's independent, whereas you'll scale exponentially if you assume things are all related in a typed way. The conditional of x given y is defined as the probability that x and y are both true divided by the probability that y is true. So it's the fraction of the times when y is true that x is also true. If you manipulate this definition by bringing y to the other side, then you get that you can write the joint, and this is general, for any joint distribution between two variables, you can write it as the product between just a marginal distribution over one variable multiplied with the conditional of the other variable given the first one. If x and y are independent, namely this holds true, if you substitute that in this equation, you'll see that the py cancels out, and you get that the probability of x given y is just the probability of x. That also corresponds to your intuitive notion of independence, right? If you say, once I know what y is, it doesn't change anything about what I think x would be, that means they're independent. Pretty much all the equations we'll be looking at going forward hold true for both discrete distributions and continuous distributions. The only difference in notation that we have when we try to be explicit is a capital P versus a small p. There is really no fundamental difference in most things we consider. So, for example, all these equations here are just the same. You need to be a little careful, I guess, with things like this, where you divide by a probability. But these things work out just as well for continuous distributions. Let's put them in parallel. So, if we have a discrete distribution, one property we have is that it sums to 1. Continuous distribution, it integrates to 1. So what's the difference? We changed Greek way of writing an s with a sigma into something that looks like a Latin way, but with a long stretch in the middle, s. And we add a dx here, which says we're integrating over x, whereas there the x is at the bottom of the sigma. But really it's the same thing. Also mathematically, of course, it's the same thing. Then for a marginal distribution, given a joint, how do you find the marginal for one of the variables? You sum out the other variables. So in discrete case, you sum it out. Continuous case, you integrate it out. Again, just replace the summation with an integral. If you are happier working with integrals or happier working with summation signs, probably any problem you look at, you can first work with whichever one you're happier with, and then if you need it continuous instead of discrete, just swap every summation for an integral, and most likely everything will work. Then, if you want to, let's say you don't have the joint, but you have this other representation that can give you the joint, the marginal for y, and the conditional of x given y, then we can do the same kind of summing out over y to get the marginal for x, and we can integrate out in the continuous case. Okay, so one way to manipulate these formulas we've just been looking at that will come back the most, since there will be two formulas coming back the most in this class. This one here, where we go from a marginal over one variable, the conditional of the second variable given the first one, to a marginal over the second one. And the other formula that will keep coming back is this one here. It's called Bayes' formula. And what it's saying is that since there's no real difference between x and y fundamentally, we can write the joint between x and y just as well this first way as the second way. Both of these hold true. Then, because these are both equal to the joint, they're equal to each other, and you bring py to the other side, to the bottom here, and what you get is that now, if you have access to the conditional of y given x and some marginals, you can find the conditional of x given y. This is actually really important. So what this will be in our case will be something like you have some prior information of what the state of your robot is, or prior information of what the map of the world looks like. Then you'll get some measurements for which you can evaluate. Y will be a measurement. You'll say, given, let's say, the state of the robot, how likely are the measurements Y? That's something you look up in your sensor spec. And then we'll figure out how to find this on one of the next slides. Essentially, you turn your prior and your sensor spec into a posterior over the state of the robot given the new sensor measurements in your prior. So how do we deal with normalization at the bottom here? So it turns out if you look at this, you want x given y, and typically what you just have a prior for x, which would be the state of your robot, and you have a sensor model of y given x. You wouldn't have access to the marginal for y. Turns out it's pretty easy to compute. So if you look at the marginal for y, using the law of total probability, you can compute it from the joint between x and y and summing out x. And for the joint for x and y, we use this formulation here, which has the prior for x and the likelihood of the measurements. How do you do this in practice? If you're given, let's see, typically what you're given, let's be very explicit, you're given px and py given x, and you want to find px given y. And the practical way of doing this, to use this formula, would be you first look at all x, and you essentially compute the joint probability of x and y. Once you have the joint probability of x and y, you don't have the conditional of x given y, but all I need to do is now renormalize, and you can renormalize by just summing all of the auxiliary variables you just computed, and then divide by that sum. In a lot of the slides, you'll see this eta pop up, and essentially what it means is it says something like p x given y equals eta and then some expression. What it means is that the expression on the right-hand side, if you look at it, for all instantiations of the variable on the left-hand side, it will not sum to 1. It will sum to something different. And the eta is assumed to be the sum of all the right-hand sides, and 1 over the sum of all the right-hand sides, which normalizes your distribution. A slight modification to what we just saw, which we'll use perhaps even more often, is the idea that you can, if you go back to all the previous slides, and any time there was an expression, any kind of expression, something with a probability and an x and a y equal to some other expressions, whatever, and there's some other y here maybe, and then there's some x appearing here. You could introduce another random variable, z, and you could just in every expression add on, this is not a particularly good marker. No, there's a better one. Next time there will be a better one. You can add on a z in every one of these expressions, which essentially comes down to saying we've observed some fact about the world. Instead of considering the entire omega as what we're working with, we're slicing out only that part of omega where z is true. And then, given that we're only looking at that part, all the same expressions go through. Essentially, your meaning of your random variables is now only the part of the region where z is true. So that's what's happening here. We have a standard expression. We had a standard expression for x for the distribution for x, which is if you had an auxiliary variable z, the marginal for x is just, and it starts here, the marginal for x is just integrating out over z, the joint between x and z. You can also write this in this way, where you have the marginal for z and the conditional of x given z. And now what happens in the next line here is that we add a conditioning bar and we add conditioning on y everywhere. If you already had a conditioning bar, you don't write two of them. Just the way people write it is with a comma between all the ones you condition on.
I'm sorry. Regarding that notation, that is x given that y and z have a certain value, or is there any difference by saying x given y and y given z? Does that change at all?
So your question is, what does this exactly mean?
Yeah.
Right? So what this exactly means is that let's see if we can write one more time with this. Originally you considered the entire set omega, and it's implicitly assumed here that when you condition, let's say that it takes on a particular value, so let's say this area is where z is true, and originally your x could take on two values, let's say. There was a x1, which is the top part, and x2, which is the bottom part. And conditioning on z, this particular value of z means that now you consider this as your probability space, and now the relative volumes might have changed for x1 and x2, because you completely discarded this part. If there's now also a particular value of y that you care about, and maybe y partition the space in some other way that maybe runs through this here, and everything on this side is y is true, then conditioning on z and y would mean that you restrict your attention to this part of the space where they're both true. Okay. There's perfect symmetry between the two here.
Yeah. Okay. So I could probably write that same expression with times y given z. The last one. I could multiply.
Oh, could you make this a y given z?
Yeah, dy, right? I could probably.
Yeah, you could do that, but then you also need a z here. Then you'd have px given z.
Okay. All right.
And you need to perform the integral of y.
Yeah, so the suggestion was essentially to swap the roles of, you can swap y and z everywhere and you get an expression that's true again. But if you just swap them partially, it won't work out. Except in this particular spot where it doesn't matter in which order they appear.
Okay.
So here's Bayes' rule with the additional conditioning. So in this case, the standard Bayes' rule we had was x given y equals y given x times prior for x divided by the normalization constant. Now all of these just have an additional conditioning on z. Yes?
But what if we don't have a prior? Is there a way to still come up with this?
That's a good question. I think that'll become more clear when we do some examples. If we get to the sensor models and we try to apply them, I think it will be clear what you need. You can only apply this if you have some prior, so you somehow need to come up with a prior. You can come up with it by collecting data or from first principles. The nice thing is your distributions, for many things, your distributions don't need to be perfectly accurate. Right? If you reason about coin flips, but your coin happens to be 0.49999 instead of 0.5, probably most of the reasoning you do with the coin flip will still be fairly good for what you're trying to achieve.
Are there any frequentist methodologies to get this distribution without prior?
It's a good question. So I guess in the frequentist case, the assumption is really that there is some unknown variable that you don't know, and that's, let's say, the probability that if you flip a coin, that it will come out heads, and you assume you don't know it, but it exists. A lot of the work we'll do we'll not necessarily make that assumption that there is such thing that exists. Often, what it even will mean, the probabilities we work with, they'll be essentially beliefs. It's the best you can know about the situation, but it might be a situation that can never be repeated. So it's not the kind of thing where you can run the experiment necessarily many times and measure how often the outcome is a particular thing. It's the way to interpret those. One way to interpret them is to say the belief corresponds to if you had to make bets based on what you pretend is your belief. You can design a betting system such that your beliefs have to reflect as well as possible what you think is the likely outcome from just a single time something happening. Any other questions? Okay, so once we are conditioning on the additional variables, we can again, as I said, the additional conditioning doesn't change much. Now everything works. You can now say, but you can now do something that involves three variables, which is you can say x and y are independent, only conditioned on you knowing what value z is taking on. So you could think of something like if you perfectly knew, let's say in this case z could be the position of your robot. And you could have two measurements, x and y, of the position of your robot. Maybe one based on a camera system that you built, another based on a GPS. And if you know exactly where your robot is, then knowing the GPS measurement will not affect anything what you believe your camera measurement will be about the position of the robot and the other way around. So both measurements have become independent once you knew exactly where the robot is. So mathematically what you have is x and y are independent given some third variable z if the probability of x and y given z is the same as the product of x given z and y given z. Equivalently, same equation as before. If you just work out a little bit of math, you'll see that you can say equivalently, probability of x given z is the same as probability of x given z and y. Saying that once you've seen z, also observing y does not change anything about what you believe about x. And similarly here, swapping the role of x with the role of y. And this will be something that's much more often true than full independence. So it turns out the assumption of full independence is great in the sense that when everything's independent, your representation will scale really nicely for every variable. You have its own representation, and another variable just adds the same amount of storage to it. But the problem with complete independence is that now observing one variable doesn't tell you anything about another variable. So once you have complete independence, there's not much you can do based on your sensors and say something about the state of robot or the map that you're building could be modeled by. Conditional independence allows you to keep some dependencies around and at the same time still have a very compact representation. And that will be the type of independence that we'll see the most. Okay, so here's a very simple example. Let's say your robot is standing in front of where it knows there's a door, and it gets a measurement z. And now that measurement z could be something from a scanner, or just some reading, let's say the distance reading from a laser rangefinder. And now the question is, what's the probability that the door is open given you measured that distance reading? That's a hard question to answer. You don't have enough information to answer this question because it could be that this is a door that's always locked and so it's going to be closed no matter what the reading is. You don't want to change your mind about that. It could be a door that's always open. It could be a variety of things going on with this door that would affect the probability of it being open given some measurement. So the way, this is a typical Bayes rule example, the question we want to answer is some diagnostic question. What's the probability that the state of the world is the door is open? And given that we got some sensor measurement in, what's much easier to come up with is causal models. Those are models that say, given a particular state of the world, what will my sensor read off? or what is distribution over measurements for my sensor. Those are much easier to build. You could go stand with your robot in front of the door, and you could have the door open 100 times, close 100 times, and for each of these cases measure what is the reading, and that could give you a reasonable estimate of distribution of readings of your sensor when the door is open, when the door is closed. Now to apply Bayes' rule, the causal knowledge is not enough. As Amir mentioned, you need some